Look up at the night sky, and it feels entirely static. The stars appear anchored in place. But that stillness is an optical illusion. The space between every distant galaxy is actively stretching apart in every direction. If we rewind that motion, watching those galaxies pull closer and closer together, we eventually hit a limit. Roughly 13.8 billion years ago, the entire cosmos converges. This visualization clarifies the mechanics of that beginning. Popular models often mistake the Big Bang for an explosion of debris into a pre-existing empty room. The reality is that space itself acts as the 3D grid stretching out, creating new physical distance between fixed points. To understand how this expansion began, we have to examine the specific fraction of a second before the cosmic clock started ticking. In the theorized state immediately prior to the expansion, the universe was a cold, featureless void. It was empty of all matter and light, permeated only by a highly unstable field of vacuum energy. This instability triggered a phase called cosmic inflation. This vacuum energy forced space to grow at a violently exponential rate. The mathematical scale is staggering. The universe doubled in size at least 80 times in less than a trillionth of a second. A patch of space the size of a grapefruit suddenly stretched to encompass the entire volume of our observable universe. This fleeting expansion locked in the vast physical dimensions and the flat geometric shape of the entire cosmos. When inflation stopped, that stored vacuum energy dumped directly into space. It transformed into a superheated plasma of radiation and newly formed particles. This created an immediate war of attrition. Matter and antimatter particles annihilated each other upon contact, but a slight numerical imbalance allowed a tiny fraction of normal matter to survive, roughly one surviving particle for every 30 million destroyed. By the 3-minute mark, the rapid expansion forced the overall temperature of the universe to drop significantly. That cooling allowed surviving protons and neutrons to fuse together in a process called Big Bang nucleosynthesis. These were the first atomic nuclei, mainly hydrogen and helium. In a span of just 180 seconds, the physical forces of the early universe successfully forged the primordial hydrogen and helium that would eventually fuel the birth of the first stars. For the next 380,000 years, the universe remained a super-hot, opaque fog of plasma. Light was effectively trapped, unable to travel to significant distances without bouncing off free electrons. Eventually, the cosmos cooled enough for a mechanism called recombination. Loose electrons locked onto the hydrogen and helium nuclei, forming the first stable neutral atoms. With the free electrons cleared away, the thick plasma became transparent. For the first time, light could travel unimpeded. We detect this escaped light today as the cosmic microwave background. This radiation is still traveling through space, billions of years after its release. The cosmic microwave background serves as a physical fossil, the literal, observable afterglow of the early universe. Even with the fog cleared, the universe entered the Dark Ages. For hundreds of millions of years, the cosmos consisted of expanding clouds of invisible gas, with no starlight to illuminate them. Dark matter acted as a heavy, invisible scaffold during this time. As this simulation shows, its immense gravity overpowered the outward expansion, pulling diffuse clouds of gas into a dense, interconnected cosmic web. As hydrogen gas pooled inside these dark matter gravity wells, the intense compression created immense heat and pressure. This pressure triggered nuclear fusion, igniting the first stars. Gravity eventually organized these stars into the first primitive galaxies. The mechanical forces of gravity successfully organized a chaotic soup of gas into the highly ordered cosmic structures we see today. Those early stars forged the heavier elements, like carbon and iron, that eventually build planets and the building blocks of life. But modern observations reveal a cosmological anomaly. While gravity's inward pull should slow the expansion, the universe is actually moving apart faster and faster. Scientists call this dark energy. This diagram shows the universe's complete history. 5 billion years ago, dark energy began to overpower gravity. We see that acceleration here in the flared curvature at the timeline's far right. Today, the dominant force dictating the mechanics of our entire universe is an invisible energy actively tearing it apart. This accelerating expansion raises a profound question about the ultimate fate of the cosmos. One possibility is a big freeze, where galaxies drift out of contact and stars burn out in isolation. Another is the Big Bounce hypothesis, suggesting a future phase of contraction and a cyclic restart. The Big Bang persists today as an active, measurable expansion of the space surrounding us. Humanity exists in the exact cosmic window where we have both the light required to see our origins and the capacity to comprehend the scale of our existence.